In this video, we are going to define what data science is, its impact on today's world, and which aspects you should consider when you implement your own projects. At the heart of data science is, of course, data. We all produce it. Each link clicked, each search query, every movie watched, every photo taken, every message sent, or even every location visited adds to the enormous digital footprint that we all leave behind. Sensors are all around us, which produce data. There is an increasing number of sensors that are monitoring various aspects of our lives. Physical infrastructures we share, like buildings, bridges, tunnels. On top of that, sensors help offering energy-saving solutions like automated lighting, temperature control in our homes, cars, or offices. Sensors are also used in maintaining public safety and road safety, such as video cameras for security and traffic control, and so on. And as time goes by, we will have more and more sensors which are generating more and more data. So, without a doubt, you have previously encountered data science in a variety of ways. You are dealing with data science products when you use search engines to get information online or ask directions on your phone, but you probably knew this already. For many years, data science has been the driving force to ease many of our everyday activities. The majority of the scientific techniques that underpin data science are not novel. Rather, they have long been available and were just lying dormant, waiting for all these modern applications to be created. Data science is commonly defined as a methodology by which actionable insights can be inferred from data. You will hear a lot the term actionable insights from me during this lecture, and you will understand later why. But now let's take a closer look. What is really data science? In short, data science is a combination of computer science and IT, mathematics and statistics, and domain or business expertise. And they all help to extract meaningful insights from data. Looking at this Venn diagram on the right side of the slide, we can dissect briefly how each of these domains contribute to data science. So, from the computer science part, for instance, we employ machine learning algorithms and high-performance computing technologies to deal with scale. From the statistics side, we have exploratory data analysis, significance testing, and visualization. Then from application domains like business, medicine, engineering, or other sciences, come challenges that drive us and the evaluation standards to assess the results once the challenges have been tackled. Data science is about turning data into actionable knowledge. If a data scientist cannot take the results of their analysis and effectively communicate them to decision makers, then they have not turned data into actionable knowledge, and consequently, they have not achieved their goal. Even if the insights they have are brilliant, if they are not sensibly shared with those who need them, they have very little impact in the end. So, something to remember that might not seem at all that intuitive in the life of a data scientist is good communication is essential for working with data. And now, let's look at the data science lifecycle. As previously mentioned, the lifecycle of a data science project may vary somewhat on a case-by-case basis with every project. After all, some companies require a minor data science implementation, while others are looking for really a company-wide development. Whatever might be the case, there are 6 steps that you can expect to go through. And these 6 steps might be mashed together, or some steps might be missing in certain situations throughout your career, but you will sooner or later go through all of them. First of all, let's briefly define the data science lifecycle. So it is a systematic approach to extract value from data. This may sound like a very business-oriented definition somehow, but it is, however, applicable in any domain. It provides a framework, if you will, for data scientists to follow from problem formulation to deployment. And now let's look at the first step in the data science lifecycle, and that is to define the problem that needs to be solved. This involves clearly articulating the business objective and understanding the key requirements and the constraints of the project. Two main issues that need to be established before anything else are: what are the questions that we are aiming to answer? And the second one, what are the challenges that we need to address? Now, let's take a step back and think of actionable insights. A well-defined problem provides a clear direction for the data science team and helps data scientists to focus their efforts on finding those actionable insights. Problem definition helps to manage expectations by establishing realistic goals and timelines for the data science projects. And there are some techniques that we can use for effective problem definition. And some of these techniques are stakeholder interviews, if you have the chance to do them. So you engage with key stakeholders and try to understand their requirements, their expectations, and their main concerns. A second technique is problem framing. So you have a bigger problem that you somehow break down into smaller, more manageable subproblems. Then you need to have some defining success criteria. So you have to establish clear and measurable criteria for evaluating the success of your project. Otherwise, you will not know if the project succeeded or not. Then you have to set up priorities. You have to identify the most important aspects of the problem that needs to be addressed first. Also, you have to document requirements, documenting the problem statement, the goals, and the constraints, and make sure that they're all clear to all the team members and everybody is aligned. Then let's go to step 2. Once the problem has been defined, the next step is to collect and prepare the relevant data for analysis. This involves identifying data sources, collecting data, and transforming it into a format suitable for analysis. Data collection is a critical phase in the data science lifecycle, as is the quality and the completeness of the data, which directly impact the accuracy and the reliability of the results. We can collect data from various sources that include internal databases in bigger companies or external APIs, web scraping, and surveys, and we will be dealing with some of these during the course. During the data collection process, it is essential to ensure that privacy and security of the data are dealt with, because sometimes there is sensitive or personally identifiable information. Data scientists must also consider data governance and compliance requirements, such as data protection regulations. And once the data is obtained, it's time to explore and clean it. In this phase, data scientists can perform various tasks like data integration, combining data from different sources, and resolving discrepancy or different conflicts between different data sources, feature engineering, creating new features that capture relevant information for the project, data reduction, reducing the dimensionality of the data to focus on the most important variables. We're going to deal with all of these: feature engineering, data integration, data reduction throughout this course. Data preparation might not seem like the most fun part of data science, but it is often the most time-consuming aspect of the implementation. But it is one that should be approached very seriously because it can really impact the results of your project. Now let's move to the third step. The third step is exploratory data analysis. So once the data has been collected and prepared, the next step is to explore and analyze it. This involves applying statistical techniques and data visualization to gain insight and identify patterns and relationships. The significance of data exploration is really cannot be understated. It's a crucial step in the data science lifecycle because it allows us to understand the characteristics and the particularities of the data. Through data exploration, we can uncover hidden insights, identify outliers or anomalies, validate different assumptions that we have or our stakeholders have about the data. And it can help also with potential data quality issues or biases that we can find out. Visualizing the data and conducting exploratory data analysis helps us to get an overall understanding of the dataset and can make informed decisions about future analysis down the line. And there are some methods that come mainly from statistics that we can employ here. So we can have descriptive statistics like calculating different summaries, like mean, median, standard deviation, and so on to summarize the data. We can have basic statistical models like regression or sometimes series analysis to uncover different relationships and make initial predictions. We can employ data visualization to create charts, graphs, interactive visualization for making the data more presentable in a meaningful way and engaging way, for instance, for our stakeholders. Or machine learning, using some machine learning algorithm to identify patterns, to classify data, or to make basic predictions. Now, let's move to the fourth step. The fourth step is data modeling. In this step, data scientists develop and refine predictive models based on the insights gained from the previous stages. So now, when we know the data a little bit better, we can choose from a wide range of models, which include linear regression, decision trees, neural networks, support vector machines, and many more. In the next step, the model evaluation and testing, we can evaluate the performance of a data model by employing various metrics like accuracy, precision, recall, F1 score, and so on. These metrics quantify the model's predictive accuracy and allow for the comparison of different models or approaches. Data scientists should also perform a thorough analysis of the model's strengths and weaknesses. So this would include assessing the potential biases or errors in your model, determining the model's interpretability, identifying areas for improvement, and so on. Model evaluation is done usually either through holdout method or cross-validation method. During the holdout method, the dataset has to be divided in two subsets, with one of them being used for training and the other one for testing. Usually we have three datasets, actually. One for training, one for testing, and one for validation. But here we mean that training and validation are both part of the training part of the holdout method. On the other hand, we have cross-validation, which is more generalizable, and this is assessed by splitting the datasets into K groups and then using one for testing and then the other ones for training. This process is repeated so that each of these groups has been used for testing. So each of the K groups has been used for testing. And then the sixth step is deployment and maintenance. So there are different deployment strategies like batch processing, where you implement the model periodically to analyze large volumes of data in batches. And this is usually suitable for scenarios with less urgency. Then we have real-time processing, where we enable the model to process data in real time. And this provides instantaneous insights and predictions. And this is used usually for applications that require quick responses. Then we could have cloud deployment. So we're leveraging here cloud platforms for deployment, and this offers a lot of scalability, flexibility, accessibility, and this facilitates easier updates and maintenance. And then when we think about continuous monitoring and maintenance, so once deployed, continuous monitoring and maintenance are essential to sustain the model's performance. There are some key considerations here to include. Performance monitoring, so you have to regularly assess the model's accuracy and responsiveness to ensure it aligns with the expected outcomes. And then there is data drift detection. Here you have to monitor changes in input data distribution to identify potential shifts that might impact the model's performance. And then updating the models. So periodically, you have to update the model to incorporate new data, to adapt to challenging patterns, to improve the predictive capabilities. And not in the least, we have to think about security measures. So here we have to implement robust security measures to protect the model and the data, especially when dealing with sensitive information. So talking about sensitive information, data drift, and so on, security measures, let's look more into data governance, because we mentioned data governance in the beginning of this video, and now we're gonna delve into it a little bit more. So what is data governance, really? In short, data governance is a set of rules, standards, and processes which define how data is handled. It includes various concepts like collection, use, sharing, and protection of data. What is the goal of all of this? Well, to maximize the quality of the data in order to increase the relevance of the analysis. A data governance strategy is essential today in the face of cybersecurity, when we have to comply with various standards and laws. For instance, in the European Union, companies must protect data cyber attacks, but also they have to ensure that the privacy of individuals is maintained as required by the GDPR for European Union countries. In addition, data governance is necessary to sort out the data relevant and then declutter the storage systems from superfluous information. And now you might wonder, okay, but what is the role of a data scientist in the implementation of this strategy? Well, employing data governance helps us make sure that data is consistent, is trustworthy, doesn't get misused, and we can do so through a series of aspects that we're going to discuss now. So let's start from data cataloging. What this means is an effective data governance, which is done through knowledge of the data that exists within the organization. So we essentially centralize the data in a repository and document all the organization's assets and all its metadata. A data catalog, anyone can access it to quickly discover, understand, and access the data they need. This helps organizations that to improve their data management, enhance collaboration, reduce the redundancy, and ensure proper controls. But not everybody can access everything, and we're going to talk about this a little bit later. The second one is data classification. Given an increasingly exponential growth in data, we are concerned about protecting sensitive data, mitigating risks, and ensuring data quality. A robust data classification system reduces risks and ensures data quality and protection at scale when you go from a small model to a big model, from a small amount of data to a big amount of data. The third aspect is auditing. So effective data access makes auditing a critical aspect of the data. This is done by understanding who has access to what data and by tracking recent access, identifying users or groups of users who have access to data, but maybe they shouldn't have access to that particular data, and adjusting their access, minimizing in this way the risk of data misuse. This plays a very important role in implementing, for instance, GDPR effectively. Now, the next aspect is data discovery. With a vast amount of data, it's important to make data easily discoverable for analytics, AI, or ML use cases. This enables us to easily locate data assets across an organization or collaborate between different projects or innovate quickly and efficiently. This helps to prevent data duplication, which can be problematic as it costs more money to keep on having data that we don't need and may lead to governance challenges at different security levels. Now, data sharing. Data sharing is very essential for collaboration. In many projects, this is a demand really for different organizations, even in the university, even in research groups. But we need to securely exchange data because it might be really sensitive if we talk about medical data, for instance. So we have to maintain control and visibility of how sensitive information is used. It is essential for organizations to invest in open format, interoperability, and so on. Then the next aspect is data lineage. Data lineage helps us ensure data quality and trustworthiness. And this is done by providing a better understanding of data sources and consumption. It captures relevant metadata and events throughout the data life cycle. The second last step is data security. Here we have to think about data access management, which is crucial for data security and also for data governance. A good data security governance program includes access controls that define which groups or individuals can access what data. And these controls can be very, very specific. They can go down to the level of the individual record or file. And last but not the least, data quality. Here we have to ensure that high data quality is permeating across analytics, and we make informed decisions and we are cost effective. Data quality directly impacts the reliability of data-driven decisions, so it's a key aspect in data governance. To maintain effective governance, we must prioritize the evaluation of key data quality attributes like accuracy, like we talked before, completeness, the freshness of the data, and the compliance with the data quality rules. And now let's look at some data science applications. So data science applications are varied, and we're going to list a few in a second, but we have to remember that they are not exhaustive at all, and they're just some examples of what we can achieve with data science. First of all, it's a lot used in finance. So it can be used for strategic decision making, customer segmentation, risk analysis, or algorithmic trading, for instance. A lot of the time it's used in banking for fraud detection, for credit risk analysis. For instance, if somebody wants to take a credit, there is always a credit risk analysis done based on all the data that the bank has about this person to see if they are meeting a specific set of criteria to get a loan, for instance. In e-commerce, data science is used to discover customers, to recommend new products, to analyze reviews, and then make the products better, like act accordingly with these results of the data science pipeline. Data science is used for the past 10 years, maybe, really, really extensively in healthcare. Bioinformatics is a field of its own. Drug discovery is again a field of its own. Medical image analysis. Nowadays, with the new dawn of NLP, we are seeing a lot of virtual assistants that are used in healthcare. In manufacturing, we can use data science to predict potential problems in different monitoring systems for anomaly detection. It has been used in predictive maintenance for maybe the last 20 years very successfully. And last but not the least, in autonomous vehicles, for instance, in autonomous cars, in autonomous maritime vessels, for vehicle monitoring systems, for enhancing passenger safety and passenger experience. For instance, on these big ships that you see that are going from Turku to Stockholm and so on. And now let's look at three essential aspects of data science. First of all, let's look at reproducibility. Reproducibility denotes essentially a model's capacity to consistently deliver the same results for the same inputs. So you can repeatedly run your algorithm on certain datasets and obtain the same or similar results. I would like to say similar results because in data science we work a lot with probabilities, and it is highly unlikely that you will get exactly the same probability, but something very close. Then interpretability. This indicates the extent to which a cause and effect can be observed within an ML model. So in a perfect world, the inner workings of a machine learning algorithm should always be transparent. However, it's not always the case, and I can say this from experience. Data changes. Different software environments change. There are different versions of different softwares, and so on. Machine learning projects should begin with reproducibility in mind, and it should be applied to every aspect of the projects from the software and environment to the development and deployment. Reproducibility helps reduce errors and ambiguity when the projects move from development to production. Also, reproducibility ensures data consistency, which can become challenging if no one is sure what kind of results are correct, what kind of not. Maybe you have 10 different experiments, and then if it's not well documented and you don't know what dataset was used and what machine learning algorithm was used, then you have no idea what is correct and what's not correct. And reproducibility also creates trust and credibility with the ML system. So how can you achieve this? By creating a well-documented ML pipeline. And this is also where the next big aspect comes in line that we already introduced, interpretability. So this is about the extent to which a cause and effect can be observed within a system. Or to put it in another way, is the extent to which you are able to predict what is going to happen if you have a change in input or some parameter in your model. And then there is a third aspect that I would like to introduce, and that is explainability, which indicates the extent to which internal mechanics of an ML model can be explained in human terms. Explainability really means analyzing the behavior of a model to understand why a given course of action was taken. Now, interpretability and explainability are often used interchangeably in the literature. And in some cases, it's easy to miss the subtle difference between them. But let's think of it this way. Interpretability is about being able to discern the mechanics without necessarily knowing why. And then explainability is about being able to quite literally explain what is happening within your ML model. This was my introduction to what is data science. I'm looking forward to see you in the next video.